Hi Year 12. I'd like to revise your final exam that you did at the end of the preliminary year last term. It was a shortened exam. It was 1 hour and supervised at home, and it was a closed book exam. So the first question in the multiple choice was which best describes the term voltage in an electrical circuit. And as you can see here, B is the correct answer. Voltage is the electrical pressure. It is the pressure that actually drives the current through the electrical conductor. Question 2, which are all vector quantities? C here is the correct answer. Of course, force, load, displacement, and weight are all vectors. Distance is not a vector. Mass is not a vector. And distance down here is not a vector, and neither is time. Question 3, what is necking in a tensile sample? Necking occurs when the tensile test piece is just on the verge of failing, and you get a sudden reduction in area, cross-sectional area, at the point of failure. And so, as you can see here, A is the correct answer, the reduction in area at the point of failure. Question 4, which forming processes produce grain flow in materials? Now, as you know, grain flow is when you apply a force to the metal and it just flattens the grain, and so you get these elongated grains which form a sort of a fabric in the metal, and it strengthens the metal, particularly in the direction of grain flow. And so B is the correct answer here. You've got to apply a force to the metal to deform the grains to form grain flow. And so rolling, forging, pressing, and drawing are all processes that produce grain flow. Casting is incorrect. Tempering is incorrect. Cutting is incorrect. Fabricating is incorrect. Welding is incorrect. Thread rolling, you get grain flow. Drawing, you get grain flow, but shell molding, you do not get grain flow in that. Question 5. You've got two forces here, and you've got to find the resultant vertical component and horizontal component of these forces. So in the solution here, if you put your vertical axis here and you draw a line across here, you will get the vertical component, which will be 200 sine 60. So there we have 200 sine 60 there. So we're saying the sum of the vertical forces equal this, and we're saying up is positive. And then this one here is going down, so you'll have that force going down there, and that will be 100 sine 20, and you subtract that because it's opposite sense, and you get 139 kilonewtons. And the same thing with this horizontal component here. You've got that horizontal component there, which will be 100 cos 20, and this will produce a horizontal component, and that will be, the 200 will be going out there like that, and that will be 200 cos 60. So down here, we've got the sum of the forces in the x direction equals 200 cos 60 and minus 100 cos 20 because it's going in the negative direction, and so you get 6 kilonewtons there. And so you look up here and you see that C is the correct answer. Question 6, two forces, 100 kilonewton, 200 kilonewton, act vertically and horizontal on a pin as shown. What's the resultant force? So this is how you get the resultant force. So you can either do it graphically or analytically, but it's probably easier to do it analytically. And so you've got 200 going to the left, 200 kilonewtons, and you've got 100 going to the, I'll just get this, to the vertical, and then you just complete your parallelogram, and that will be the resultant there. It'll be R bar, and you've got to, of course, find the angle, which will be theta there. And so this is what I've done here. So down here, there's Pythagoras. You know what Pythagoras theorem is, the square of the two forces. You add the two together, you take the square root, and you'll get the diagonal, which will be the resultant, and it works out to be 223.6 kilonewtons. And you've got to find the angle, and angle here is 100, tan theta equals 100 over 200, and you get 26.6. And as you can see here, it's going upwards to the left, and so A is the correct answer there. Question 7, what's the main reason why buttresses were built into high stone walls on ancient buildings? Well, when the ancient builders just used sandstone, all they were doing was just using the mass of the sandstone to give the wall its integrity. They were using probably pretty weak concrete, and the higher they went, the more unstable they became. So they put a buttress on the outside like this to make the walls a lot more stable. And of course, we don't have to do that now because we use, for example, concrete blocks that have, and this is what one looks like. And they build these up, and these are hollow on the inside, and they're held together with concrete, but they've got bars, not a starter bars, which are steel bars going up through them, and they've also got steel bars going along them. They've got actual grooves in them to allow the steel bars to reinforce the wall. Then they fill the holes with concrete, and down the bottom of the block at the bottom, you've got special blocks which have a cutout in, and then when they're forcing the concrete down, you see the concrete coming out here, and you know that the wall is totally compacted with concrete. So you don't need buttresses on that. And so the answer to 7 is to provide vertical stability and rigidity to the wall. Okay, next page. Which material is easiest to deform? You know that face centered cubic has got 4 atoms per unit cell, and body centered cubic has only 2. Cementite is a very difficult material to deform, Fe3C, and perlite is a layered structure of cementite and perlite, and because face-centered cubic has more atoms than body-centered cubic, it's easier to deform, and so face-centered cubic austenite is the most ductile material there. Question 9, a lever pivoting at A has 100 kilonewton force balanced by a force F acting at 45 degrees as shown. What's the force at F so that the lever maintains equilibrium? Well, the best way to do this is to break that force up into a vertical component. And you don't have to worry about the horizontal component, because by the principle of transmissibility, it'll go through that point there. And because it has no lever arm, it creates a zero moment. And so this vertical force here that I've drawn down here, it is F sine 45, which is 0.707 F. And so you multiply this force, which is 0.707 F, which is this one down here, by the perpendicular distance that it is from the pivot point, which is 0.6 of a meter. And that's going to go anti-clockwise. That force is going to go around like that. It's going to go anti-clockwise. And so that will be negative, which I've put here. And then this force will go clockwise. And I've said that in the statement here, the sum of the forces about A equals 0. I've got to use these annotations because Blackboard no longer has a pointer, which is a bit of a pain. So you have to use the annotations on it now. So you've got 100 multiplied by 0.35, which equals 0, and you get the force of 82.5 kilonewtons. And so C is the correct answer there. Next question. Question 10, a tensile sample, diameter 15 millimeters and 150 millimeters long, extends 185 millimeters at fracture. What is the strain at fracture? Now you know that strain is the change in length over the original length. And put your data here. Make sure you put your data, because it's a double check, and also the markers can check if you make an error. And you might get full marks if it's a transposition error or mathematics error, because if you've made a maths error in the same question part above, you can't be double penalized. So see the diameter here that they've given you, 15 millimeters. That's a spurious value that you don't need. And you really have to know what you're doing with this to eliminate that. And so the change in length is 150 taken away from 185, which gives you 35. And the original length is 150. And so when you have millimeters like this here, and that's a good way of doing this, you've got millimeters there and millimeters there, they cancel. And it's a ratio. And so generally it's given as a percentage. And you can see that you've got a percentage here, and you work out that this value here, keep forgetting there's no pointer, is 0.233, multiplied by 100 to convert it to a percentage, and so it's 23.3%, and so D is the correct value there. Next question. You've got to find the coefficient of friction between the block and the surface on which it rests. And you can see here the solution, force of friction equals mu n, and you get that from your formula sheet, but you should be able to remember that. You'll be having a formula sheet from now on for each exam. And so transpose the formula, mu is equal to force of friction over normal. Put your data here. Make sure you put your units as well. And so coefficient of friction is equal to 175 over 500. And so it works out to be 0.35. So C is the correct answer there. Which process is mainly used to form polymers, which is question 12. Drawing is not mainly used for polymers. Die casting can be used for metals, mainly used for metals. And shell molding is used mainly on metals, and injection molding can be used on metals and polymers, but it is mainly used on polymers. So D is the correct answer. 13, which is a natural composite? As you can see here, timber is the natural composite. It's composed of cellulose fibers and a lignin matrix. Question 14, why is an alloy stronger and less ductile than a pure metal from which each of the metals in which the alloy is derived? So that if you've got a pure metal, this is what this structure looks like. You've got one element in the structure, but if you have a alloy, you can upset the slip planes by either putting a huge element, the alloying element, in the structure, which will inhibit the movement of slip planes. Here you've got nice easy slip planes there, but there's no slip planes over here. There's no slip planes. And so that, or not very many. So D is the correct answer here. The alloy has stranger atoms and offers greater resistance to the movement of dislocations. And so that there is the stranger atom. They can be either much larger than the parent metal atoms or much smaller, which will inhibit the movement of dislocations. Next page. What is the resistance? You know that resistance is equal to voltage over amperage. It's given to you in the formula sheet. And so that is basically a simple calculation. Put your units and values here. So it's 240 over 15, which is 16 ohms, which the correct answer is A. Question 16, which correctly identifies metals 1, 2, and 3? Well, metal 3 here is progressive yield, and metals like aluminium, heat-treated steels, copper, brass, they have a progressive yield like this, but as you can see, they're not very stiff. You can see that this particular metal is leaning over a lot, so its Young's modulus would be quite small. This metal here is a giveaway because it's got an upper and lower yield point, so that is definitely mild steel, low carbon mild steel. And this one here, metal 1, is quite brittle. It's not strong, but it's quite brittle. And so you can easily see that D is the answer here. Metal 1 has got to be grey cast iron. Grey cast iron is quite brittle because of the carbon in the form of graphite flakes. And metal 2 is annealed mild steel, which you should know, and metal 3 is copper. So D is the correct answer there. Question 17, what's the sequence of grain change when a coal work metal is heated above the recrystallization temperature? The D is the correct answer here. As you can see, the first thing that happens to a deformed grain structure when it's being heated, it recovers. In other words, you get nucleation points occurring at grain boundaries, and then recrystallization, you get the deformed grains being replaced by the new recrystallized grains that were nucleated at the grain boundaries, and then you get grain growth. And it's important to not allow the grains to grow too much because it will severely weaken the material. Next question is question 18. What is the true stress at failure? When you're given the original diameter and the diameter at failure, you can almost be certain that you're going to be asked a true or engineering stress question. So first thing you do is that you write down your formula here, and you're asked to find the true stress. So you've got stress true is equal to load over area at failure, and put all your data down here, and notice that I've worked out what the area is there, so you don't have to transfer all this information to your equation. You've worked it out, so you're eliminating the possibility of transferring errors. And I don't put 10 to the minus 6 down the bottom here, because when it comes up, it comes 10 to the plus 6, and we just call it megapascals. So 707.4 is the correct answer, and as you can see, it's B there. Question 18 is a true stress question, which we've done. Question 19, you're given a bolt. Now, make sure you know what this means. M is metric profile, and we'll only be dealing with metric profiles. You don't have to worry about Whitworth or Sellers or British Association. We only deal in engineering studies with metric profiles. The 15 is the diameter, right? So that is phi. And this 2 is the pitch. And the pitch, as you know, is the distance between one crest of a thread to the next. And that's the pitch. Okay. And here's Z, which is the pitch, and the convention for pitch is on a drawing is pitch divided by 2, so that'll be 1 millimeter there. So let's have a look. You can see that this X is 1.8 D. So 1.8 times 15 is 27. So you look down here and see where you've got 27. We've got 27 here. Check that the other Y is 0.7 D. 0.7 times 15 is 10.5, and Z is 1. So obviously D is the correct answer. Last multiple choice, why is reuse of materials more efficient than recycling the materials? Reuse requires very little, if any, energy to reuse the product or the material, whereas recycling requires a lot of energy input into the process to get it to become a new material. So A is the correct answer there. Question 21 is you're given a bracket, and these 260 Newton forces will try to rotate the bracket anti-clockwise, but the force in the screw here will resist that by applying clockwise moment. And so the first question, A, determine the force couple system acting at A. Now the force that is acting at A is a force which is trying to shear. This is the reactive force there, but the 260 Newton forces added together, you give 120 Newtons trying to shear that force. So you say here, the sum of the forces in the y direction is equal to 60 plus 60, which is 120, and you show that it's acting down. So that's the shear force. So we've found the force. Now we've got to find the couple system. Now the couple system of these two 60 Newton forces rotating, trying to rotate the bracket about point A there, because you've got, that's called engineering acumen. You've got to know where the bracket is going to rotate about. So you say the sum of the moments about A, so you've got minus 60 multiplied by 0.98, and don't forget you've got to go right back to the point of rotation, and it's that distance there. So you've got to add up all of those values because you've got to get the correct lever arm. So that's 98 millimeters, and then minus this 60 here, and multiply by 54, go right back to here, which is 50 plus 4. A lot of you missed this 4, the thickness of the bracket. And so you get minus 9.12 Newton meters. It's a moment, so it's Newton meters anti-clockwise, and that is the couple at A. Next question, calculate the tensile stress acting in the 5-5 screw, and to find the force in the screw, you've got to take moments about the pivot point, which is pivot point A there. And so you've got your moment created by the 260 Newton forces, and so it's minus 9.12 because it's going anti-clockwise, plus the force times the perpendicular distance of that force about the point of rotation, which is this distance here. So it's 18 millimeters right to the point of rotation, equals 0. So we get a force of 506.7 newtons. Then stress. Now I haven't put where here because I did this mainly for teachers for the solutions in the independent final year 11 exam. And so stress equals load over area. Put your formula. So you got the force divided by the cross-sectional area. I haven't put 10 to the minus 6 in because I'm going to call it megapascals. And so it's 25.8 megapascals. Okay, now I'll just get rid of all these annotations because we've got to do question C, which gave most people a bit of grief, but it's not that difficult. I'll just go through it now and show you how easy it is once it's explained. Calculate the reaction force acting at A when the 260 Newton forces are applied. So if you've got two forces acting down, 60 Newton forces, you've got to have a force acting up here like this. You've got to have a force acting up there to resist these two forces here, right? And because you've worked out that this force in the screw is 506.7, you've got to have a force that will resist that force. And so if that is going anti-clockwise, this one here will be going in the opposite sense there. And so what you do is you say the sum of the vertical forces equals 0 with up positive. And so we've got the 260 Newton forces going down negative, plus I call the vertical force here FA, which is the force at A, and it's going in the y direction, and that equals 0. And so FAY is equal to 120 newtons going up. So this force here is 120 newtons going up. And obviously, this force here has to equal that force there. And so you just say down here, the sum of the horizontal force equals 0. You don't really need to put all this down here because you can see there's only one force acting. So FAX is equal to 506.7. It's going in that direction. But now you've got to complete the parallelogram and you've got to work out what the reaction is, or the resultant of those two forces. And using Pythagoras, we've got 520.7, and then you've got to find the angle here, which is theta. Right, tan theta is equal to opposite over adjacent, so it's 120 over 506.7, and it works out to be 13 degrees up to the left. And that's how you find the reaction force at A due to this force and those two forces there. Now finally, the question 22 is a graphics question, and it was pretty well done, but there were some major errors with some people still not understanding what projection is. Look, some of you are putting the front view here, and then you're putting the right side view up here, and you can't do that because these are projections on mathematical planes. As you can see in your book, if you want to turn to page in your yellow book, if you can get your yellow book now and have a look at page 7, you'll see how these mathematical planes work for third angle projection. So make sure you study that. So these views have to be directly in line with one another, so that this view here is looking in that direction and drawing what you see here. So you can't just put views all around the place. That is wrong, and it will be dimly viewed by markers. That was one thing that was done incorrectly. And now the other thing was this here, showing the thread. Look, when you show an internal thread, you make sure you put your center lines in, then make sure you put your hole in. And if you want to show a thread, you work out what the pitch is, and then you put a concentric hole around like this, and you generally leave a gap in the top left-hand quadrant. Some people leave it in other quadrants, but it's normally done in the left-hand quadrant, and that tells you what a thread looks like, an internal thread looks like on a drawing. And you can see that it's shown here, the hidden detail showing the thread going through there. The other problem is that some people showed the radius like this. Now, you don't show a radius for a hole, because that means the person that's manufacturing this has to do some mathematics to get a drill. So they have to multiply 10 by 2, and they could make a mistake. And so you're the draftsperson, you're the person that's drawing it. You have to work out all of the sizes so that there's no mathematics to be done by the person that's making the article. And so this is the correct way to show a radius. And you don't do that, you just do this. You say phi, whatever it is, phi 10. You have to show the diameter of a hole, not the radius. And the other thing that a lot of students missed was the hidden detail, just here. Okay, I hope you understand all that, and thanks for listening. Bye.